Suppose the landing works. A crewed vehicle reaches Mars, the dust settles, and the first systems wake up on the surface. The next question is not poetic. It is inventory. How much oxygen is left? How much propellant is available for the way home? How much mass did Earth have to launch just to keep the mission from becoming a very expensive campsite? Rockets are powerful, but they are not generous. Every kilogram hauled from Earth costs launch energy, cruise margin, landing risk, and storage. That is why serious Mars planning keeps returning to a quiet idea with enormous consequences. Make useful supplies on Mars. This is Path to Mars on the Quantum Files. Episode 3 is about in situ resource utilization, or ISRU. Turning local air, ice, and power into oxygen, propellant, and a more believable route home. It is not a shortcut around physics. It is a way to stop shipping the entire mission from one planet. The difference between bringing everything and making some things locally is the difference between an expedition that barely repeats and one that can improve over time. In situ resource utilization sounds like a phrase built for a conference slide, but the basic idea is familiar. Use what is already near you. On Mars, the obvious local resource is the atmosphere, which is mostly carbon dioxide. That carbon dioxide is thin, cold, and not breathable, but chemically it is useful. With the right equipment, carbon dioxide can be processed to make oxygen. If a mission also has access to water ice, that water can be split into hydrogen and oxygen. Hydrogen can react with carbon dioxide to make methane in processes related to chemistry already understood on Earth. Methane and oxygen are attractive for some rocket engines, while oxygen alone is also needed for breathing and for oxidizer. The strategic promise is simple. Ship the machinery, the starter supplies, and the power source. Then let Mars provide part of the mass. The hard part is that Mars does not hand resources over. It makes you earn them through mining, processing, filtering, heating, storage, and maintenance. NASA's Perseverance rover carried a small experiment called MOXIE, short for Mars Oxygen In Situ Resource Utilization Experiment. MOXIE was not a factory, and it was never meant to be one. It was a technology demonstration about the size of a compact appliance, built to pull carbon dioxide from Martian air and produce oxygen. It worked in multiple runs under real Martian conditions. That matters because Mars has a way of humbling ideas that only behave in clean rooms. MOXIE showed that the core oxygen-making chemistry can operate on the surface. The next challenge is scale. A human mission would need far more oxygen, especially if oxygen becomes part of the return propellant supply. It would need equipment that runs for months, not short test periods. It would need dust-tolerant intakes, dependable power, heat management, sensors, spare parts, and storage tanks. MOXIE was the match. A crude Mars architecture needs the furnace, the factory, and the inspection crew. Water changes the whole equation. If you can reach it, process it, and keep the equipment healthy, water ice can support life support, radiation shielding concepts, agriculture experiments, and fuel chemistry. Mars has water ice, but it is not placed wherever a mission designer might want it. Some of the most accessible deposits appear at higher latitudes, where sunlight, temperature, and landing conditions may be less friendly. Near the equator, conditions may be better for solar power and thermal management, but easily mined ice may be harder to confirm. This creates a real site selection trade. The best scientific landing site is not automatically the best fuel site. The prettiest flat plain is not automatically the best place to dig. Before humans rely on Martian water, robotic missions and orbital surveys need to reduce uncertainty. A buried ice map is not a bucket of water. It is a promise that still needs drilling, heating, purification, and proof. No Mars fuel plant runs on good intentions. It runs on power. Making oxygen from carbon dioxide takes energy. Mining and heating icy soil takes energy. Compressing gases, chilling propellant, moving pumps, running computers, and keeping hardware within temperature limits all take energy. Solar power has advantages. It is familiar, scalable, and already used across Mars missions. But dust reduces sunlight, night arrives every sol, and storms can darken the sky for long periods. Batteries and other storage can help, but storage has mass. Nuclear power offers steadier output and less dependence on weather, but brings its own engineering, political, and launch safety requirements. A realistic architecture may use more than one source. The key point is that power is not a side topic. It is the fuel plant's heartbeat. If production falls behind, the planets will not pause their orbital schedule. A return window can arrive whether the tanks are full or not. Making oxygen or methane is only part of the job. The product has to be stored safely, monitored, and kept clean enough for its intended use. Rocket engines are not fond of mystery contaminants. Cryogenic propellants may need low temperatures, insulation, pressure control, and boil-off management. Tanks have to survive dust, thermal cycling, and months of waiting. Sensors have to tell the truth. Valves have to open after sitting in a harsh environment. For breathing oxygen, the quality standards are different but just as serious. Nobody wants a life support system that works in headline numbers while hiding chemistry problems in the details. This is where ISRU stops sounding like a clever trick and starts looking like an industrial plant. A plant has inputs, outputs, waste streams, maintenance schedules, and quality checks. Mars will not reward a system that only proves it can make a puff of gas. The scoreboard is full tanks, verified product, and enough margin to trust the next step. It also means understanding the waste side of the process. Filters load up, compressors wear. Heat has to go somewhere. If the plant needs imported cartridges every few weeks, the shipping bill returns through the back door. A useful system closes as many loops as it can without becoming too fragile to repair. A conservative Mars campaign would likely send the fuel-making hardware before the crew depends on it. That is not timid. It is how you turn a bold plan into a responsible one. Cargo landers can place power systems, processing units, storage tanks, and construction robots on the surface. The plant can start operating during the months or years before a crew arrives. Engineers on Earth can watch performance, troubleshoot slowly, and decide whether the system has actually met its goals. If it has not, the crew does not launch into a fantasy. That approach does add complexity. It requires reliable robotic deployment, strong communications, spare parts, and the ability to handle dust and cold without people nearby. But the alternative is worse. Asking astronauts to land and discover whether their ride home is still a chemistry experiment. The summit push works better when the base camp is stocked before the climbers arrive. Good mission design keeps an honest failure branch. If ISRU underperforms, planners need options. Maybe extra propellant is landed from Earth. Maybe the first crew mission does not rely on Mars-made return fuel at all. Maybe the surface stay is shaped around verified production milestones. Every backup costs mass and money, but those costs are the price of not pretending. The most dangerous version of ISRU is not the technology itself. It is the slogan version, where a slide says, Mars will make the fuel and the architecture stops asking what happens when pumps clog, power drops, or ice is harder to mine than expected. The optimistic version is better. Test small. Scale carefully. Run before crew arrival. Demand proof. Then let local resources reduce the burden on Earth. In that form, ISRU becomes one of the most powerful unlocks on the path because it changes Mars from pure destination into partial supply chain. If Mars can provide oxygen and help provide return propellant, the mission gets lighter, safer, and more repeatable. It still does not get easy. The same planet that offers carbon dioxide and ice also throws dust into intakes, blocks sunlight, wears down mechanisms, and changes the performance of every outdoor system. Fuel is an unlock, not a finish line. Next time, we look at dust storms and invisible weather, the environmental pressure that decides whether surface systems keep working after the first good day.